Good morning and most welcome to 1290 of the Heidegger series. We have a very foggy day today. It's almost like smoke hanging closely. Oddly enough, it's lighter today than yesterday. It's still a bit warmish, although we're approaching the colder temperatures. Today I will finish off Temporal Naturalism by Smolin, and when that's ended during the lecture I will go over to continue on One Singular Universe by Smolin and Roberto Mangueira. Let's see here. I need something to stand on as well. We had gotten into time and qualia, the other aspect of the problem, so to speak. Something that I would say usually is perceived to be more philosophical. Smolin means that it is also part of physics. And here we come to the longer argument. We ended 1289 with a shorter argument, and now that's the longer version. To get into it, I will take the shorter one. Qualia can only be real properties of the world where now has an intrinsic meaning, so that statements about now are true non-relationally and without contingency. These are the case only in a temporal natural world. It has been objected that eternalists can see the history of the universe having temporal parts with intrinsic qualities. This misses the key point, which is that any reference to one of those timeless parts in a block universe framework must be contingent and relational, whereas our knowledge of qualia are unqualified by either contingency or relation to any other fact. That was the short version of the argument. Here's a longer version. We have direct experience of the world in the present moment, just as the fact that we experience is an undeniable feature of the natural world. It is also an undeniable feature of the natural world that qualia are experienced in moments which are experienced one at a time. This gives a privilege status to each moment in time. Associated to each experience. This is the moment that is being experienced now. This means that we have direct access to a feature of the presently present moment that does not require relational and contingent addressing to define it. We can give and we can define and give truth values to statements about now, which are not contingent on any further knowledge of the world. How can these facts about nature, that each qualia is an aspect of a presently privileged present moment that does not require contingent relational addressing to define or evaluate, be incorporated into our conception of the natural world. This fact fits comfortably in a temporal naturalist viewpoint, because in that viewpoint all facts about nature are situated in or in the past of presently privileged present moments, and no relational and contingent addressing is required to define those that refer to the present. This fact cannot fit into a timeless version of naturalism, according to which there are no facts situated in presently privileged present moments, except when that can be defined timelessly through relational addressing. The same is the case for Barber's moment pluralism. We can draw a stronger conclusion from this. There's no physical observable in a block universe interpretation of general relativity that corresponds to my ability to evaluate truth values of statements about now without any need for further contingent and relational facts. The block universe cannot represent now, because now is an intrinsic property, and the block universe can only speak of relational properties. Hence, the block universe is an incomplete description of the natural world. That is because qualia are undeniably real aspects of the natural world, and because an essential feature of them is their existing only in the present moment. Qualia allow the presently present moment to be distinguished intrinsically without regard to relational addressing. Any description of nature that does not allow now to be intrinsically defined is an incomplete description of nature, because it leaves out some undeniable facts about nature. Hence, the block universe and timeless naturalism are incomplete, and hence they are wrong. Seven one. Two speculative proposals regarding qualia. I would like to finally offer two speculative proposals regarding the physical correlates of qualia. Panpsychism asserts that some physical events have qualia as intrinsic properties, some of which are neural correlates of human consciousness. But it does not need to assert that all physical events have qualia. Might there be a physical characteristic which distinguishes those physical events that have qualia? According to the principle of precedence, which I discussed above, there are then two kinds of events or states in nature: those for which there is precedence, which hence follows laws, and those without precedence, which evoke genuinely novel events. My speculative proposal, the correlates of qualia, are those events without precedence. It is commonplace to observe that habitual actions are unconscious in people. Maybe the same thing is true in nature. Maybe brains are systems where a lot of novel events take place. Here is a second question raised by panpsychism. If brains have states which are neural correlates of consciousness, but consciousness is a general intrinsic property, of matter, then what physical properties correlate to qualia? Or to put it differently, in what way do the physical attributes of correlates of consciousness vary when the qualities of qualia vary? Panpsychists argue that the elements of the physical world have structural properties and intrinsic and internal properties. By arguing that matter may have internal properties not describable in terms needed to express the laws of physics. Panpsychists reserve a place for qualia as intrinsic, non-dynamical properties of matter. And I would propose to cut the pie differently. I would hold that events have relational and intrinsic properties, but relational properties include only causal relations and space-time intervals, which are derivative from them. Under intrinsic properties, I would include the dynamical quantities, energy and momenta, together with qualia. I would go further and relate energy and qualia. I would point out that the experienced qualities of qualia correlate with changes of energy. Colors are a measure of energy, as are tones. 8. Objections to temporal naturalism. I would like to close by mentioning some objections which have been offered to the arguments summarized here, and briefly indicate the response I would offer. an objective notion of the present is inconsistent with the relativity of simultaneity. Temporal naturalism assumes there is an object observer, independent distinction between present, past, and future. This violates the relativity of simultaneity, which is supported by ultra-precise tests of special relativity. Furthermore, there is the Putnam argument that presentism plus the relativity of simultaneity implies eternalism. That is the block universe. But as I discussed above, there is a formulation of general relativity which is empirically equivalent to the older one, shape dynamics, that has a preferred global simultaneity because it trades the relativity of time for a relativity of scale. Hence, temporal naturalism can be consistent with all the experimental tests of special and general relativity. Excuse me a second here. the meta-law dilemma. If laws evolve, there either is a meta-law by which they evolve, or there is not. Suppose there is a meta-law. We must ask why that meta-law. Hence, there is danger of an infinite regress. But suppose that there is no meta-law, then there are features of the world that are not explained. That is, sufficient reason is not gained. In either case, a rational explanation of the world is stymied. This dilemma is important, but we argue that it is in the class of dilemmas that are resolvable by the invention of new forms of explanation. We offer several avenues to resolve this dilemma. 1. The regress arises in a particular form of law. It can be avoided if the meta-law does not have the form of the Newtonian paradigm. For example, a statistical form of meta-law, as is posited in cosmological natural selection, by the stipulation that changes in the parameters of the standard model resulting from bounces are small and random, can provide sufficient reason for some features of those parameters. Such an hypothesis may or may not be explicable in a more detailed meta-law, but need not be explanatory. Two, we can take advantage of the weakening of the distinction between state and law to unify them, so that the distinction between them is emergent and approximate. A model illustrating this will be discussed. 3. We can posit a principle of universality of meta-laws, analogous to the principle of universality in computation, according to which any two candidate meta-laws that satisfied a reasonable set of conditions would be isomorphic in their explanatory outcome. 4. Laws may emerge and evolve with the phenomena they described, as in biology. These are avenues to explore which show at minimum that the meta-laws dilemma, rather than being a dead end, may be the key to further breakthroughs. We would suggest that the direction of theoretical cosmology in this century will be determined by which turns out to be the right solution to this dilemma. Internally inconsistent. Some philosophers offer arguments that temporal naturalism is inconsistent. Some of these date back to the old presentism, eternalism debate. Nonetheless, they are at best inconclusive because they tend to err by assuming what is to be proven. Temporal naturalism may be wrong, but it is a logically consistent position to take. Its validity will be determined by the success or failure of its empirical agenda, that is, the confirmation of predictions which follow from particular hypotheses about the evolution of laws. Here is an example of such an argument and why it fails. Temporal naturalism asserts that the present moment has special status, but it also admits that there were moments in the past and will be other moments in the future. But all these other moments will have or have had that same special status with respect to observers at those times. Hence, any special status claimed for now must apply to all moments. This argument fails because it does not respect the assumptions of temporal naturalism. Within which the italicized sentence either has no truth value if it refers to the future, or does not demonstrate that the past is the same as the present if it refers to the past. With regard to the future, it has no truth value because no statements about the future have truth values. With regard to the present, with regard to the past, it may be true that past observers gave the same special status to their then present moments that present observers give to our present moments. But this does not make the past the same as the present. All truth values must be evaluated relative to the present, and we evaluate evidence about past moments differently than we evaluate statements about the present moments. The point is that the special status that temporal naturalism gives to the present can only be claimed or evaluated in that present. It is not transferable. There may be evidence in records of past observers, but this is not the same as the evidence that comes from the direct apprehension of now. Hence, while we believe past moments may may have existed, that belief is based on indirect evidence. We cannot assign that belief that the same status as our direct knowledge of the present. To put this in terms developed above the italicized sentence requires contingent relational addressing to make sense of claims about the past, which is different from our knowledge of the present. Another argument sometimes given against the logical coherence of presentism is that no meaning can be given to the flow of time, because any claim that time flows has to answer the question of what determines the rate of the time's flow. But so the argument goes, it makes no sense to talk about a rate of flow of moments. To me, this is a pseudo problem. Temporal naturalism has no need to speak of the rate of flow of time, nor does this question need to be answered. In relativistic physics, we have a perfectly cogent notion of proper time, yet no one ever wonders about its rate of flow. Or rather, the answer is either trivial, that is, the rate of proper time with respect to itself is unity, or arbitrary, as in the rate of flow of proper time with respect to an arbitrary parameterization of a word line. A third argument against the cogency of presentism starts with the query that the instant cannot be instantaneous, because all perceptions of movement actually require a duration. The present must then be thick, that is, comprising a duration, which means we have to answer the question as to how thick is the present. This seems correct, and we propose a precise specification of a thick present within an ontology of events. Can causality be prior to law? The standard view ties causality to timeless law. Causal implication is explained by being actions of law. But if laws evolve while present events nonetheless continually give rise to future events, causality must be prior to law. Can we maintain a notion of causality as prior to law? A notion of causal inference prior to law is developed earlier. Causality is envisioned as a consequence of what we call the activity of time. This is to bring future events into being out of present events. Whereas any law is contingent and temporary, this activity of time can be posited to be the one aspect of nature that is inherent and immutable. Another reason causality must be prior to laws stems from the principle of identity of the indiscernible. This implies that all events are unique, that is, its properties, both relational and intrinsic, must be distinguishable from those of every other event. Thus, the simple statement A and B are causes of C is incredibly complex, because the full specification of A, B, and C require vast amounts of information. But if each event and each causal influence are incredibly complex, then there are no laws governing the microscopic scale that are both simple and general. we see we see already in general relativity the incredible complexity of contingent observables needed to specify and describe local events. Can eternalists believe in the evolution of laws? The point is sometimes raised that an eternalist can believe that laws evolve. In a certain sense, this is true, but this misses the point because it rests on a change in the meaning of the word evolve. What an eternalist or block universe person means by an evolving law is a dependence of the law on a time parameter which could be described timelessly. That is, an example would be a Hamiltonian. Depending on t, the age of the universe. But this is just a particular form that a timeless law could take. This is also a confusion brought about by the difference between the physicists and the philosophers' notion of the block universe. That is, an eternalist who is happy with a very weak philosopher's block universe can admit evolving laws, but the temporal naturalist, constrained by the stronger physicist block universe, cannot. What is the status of mathematics? Temporal naturalism is incompatible with Platonic and Pythagorean views of mathematics and its relation to physics. Platonism is the view that the mathematical objects exist within a separate reality. No naturalist can be a Platonist, as naturalism asserts that there is only one mode of existing, which is that of physical existence. Pythagoreanism is the view that the world, or else its history, is really a mathematical object. It is clear that a temporal naturalist cannot be a Pythagorean. In fact, what we can argue that if one only posits the reality of experience of the present moment, one can deduce that the world and its history are not isomorphic to any mathematical object. Named MO, mathematical object. For were it so, every property of nature would have a corresponding property of a mathematical object. Here is one property of the world that has no correspondent in any property of any mathematical object. That it is always some moment which is one of a succession of moments. Properties of mathematical objects are truly timelessly, that is, if true, they are always true. So for a temporal realist, the effectiveness of mathematics in physics is limited to necessarily incomplete modeling of subsystems of the universe. Hence, the effectiveness is reasonable. Wegener's worry about the unreasonable effectiveness of mathematics is physics, is resolved in physics, I think it should be. The unreasonable effectiveness of mathematics in physics is resolved by reducing out our expectations for what mathematics can represent from a correspondence with every property of the whole universe to a very effective but approximate description of the observed behaviors of subsystems for the universe. Conclusions. The main theme of this essay is that the concept of time we hold has a great influence on how we understand the core elements of natural philosophy, such as state and law. I have shown that there are different versions of naturalism which differ on the conception of time, state, and laws in ways that have strong implications for the future direction of of physics and cosmology. I argue that one of these, timeless naturalism, is at a dead end as a framework for thinking about cosmology. I gave several reasons for this, one of which is because why these laws and why these initial conditions, questions are unanswerable within it. On the other hand, I argued that temporal naturalism offers avenues to resolve these questions, and hence is the way to continued progress of science. Most of this essay briefly introduced arguments that are developed in much more detail earlier, but I used the opportunity to introduce some new themes which arose in recent works, such as the singular universe. One is a cluster of ideas connecting the uniqueness of elementary events to the irreversibility of fundamental laws and the non-relational intrinsic character of energy and momenta. I also suggest that temporal naturalism may be useful for philosophy of mind, and particularly for those interested in Chalmers' hard problem of consciousness, which is the relationship between the qualia of experience and the physical world. I argue that belief that qualia are real and are part of nature is closely related to the belief that the present moment is real. Both are direct apprehensions. Both are internal and intrinsic, non-relational aspects of nature. Hence, temporal naturalism is qualia friendly. 9.1. What is at stake? I close by looking more broadly at what is at stake in the debate between timeless and temporal naturalists. The two views explain a certain clustering of views scientists and philosophers often, but not uniformly, tend to hold on diverse issues. Thus, I have observed that those who believe in a strong artificial intelligence, AI, tend also to believe that nature is a computation in the illusory character of qualia and the passage of time. In many worlds interpretation of quantum theory, as well as in anthropic multiverse cosmologies. Those who tend to be realist about time and its passage are more likely to believe that qualia are real, that quantum mechanics is incomplete, and to be skeptical both about strong AI and anthropic multiverse cosmologies. While exceptions exist which show that these correlations are not perfect, their ubiquity suggests there is something to explain. I would suggest that what is at root in the divergence of scientific worldviews is the disagreement we have discussed here between temporal and timeless naturalism. Timeless naturalism is associated broadly with the views that the future is determined. The world is nothing but elementary particles with timeless properties, moving and interacting according to timeless laws. Novelty, agency, purpose, intentionality, will are all illusions. The universe is or is equivalent to a computer, classical or quantum. Hence, strong AI persons are also perfectly emulatable as computations. Laws and initial conditions are inexplicable except via the anthropic principle in a multiverse. That is, sufficient reason is impossible and modern science is at an end. Temporal naturalism holds instead that the future is partly open in that laws evolve on cosmological and perhaps also quantum scales. The long term evolution of the universe is not computable. The history of the universe is not isomorphic to any mathematical object. Persons have properties that cannot be captured by any computation. The brain is a physical system, but not a programmable digital computer. Laws and their initial conditions may be explained by falsifiable hypotheses, as do their mechanisms of evolutions. That is, there is much science still to do. These divergent views confront each other within the communities of scientists and underlay debates within fields as diverse as cognitive science and cosmology. I hope I have said enough in this essay to suggest that temporal naturalism is the naturalism of the future. Well, I thank you very much for that one, Smolin. Very nicely put. Just give me a second. So I will continue here with the singular universe, and we are at part 2, the one written by Lee Smolin. Yes, we continue with Smolin. But I will soon parallel him with other thinkers. Amazing, I can bend a stapler with my own nails. Need to use it as a lever though. So this is more wordy than the very condensed text we just read. We continue about the MOs, the mathematical objects. A common and widely believed example is the claim that X, the universe, is really a mathematical object. Whether that mathematical object is a solution to an appropriate extension of general relativity, or a vector in an infinite dimensional space of solutions to the Wheeler-de Wit equation of quantum cosmology, there is a big stretch from a statement of the form. Some experimental evidence concerning a specified range of phenomena is well modeled by a mathematical object, O, which is a statement that might or might not be supported by evidence, and a metaphysical assertion that the universe is really a mathematical object, which is not by any reach of the imagination a hypothesis that could be tested and confirmed or falsified. What is troubling is that the statements of the form experience is an illusion, the universe is really X, are common in religion. When naturalists make statements of this kind, they are falling for what might be called the transcendental folly. They are replacing the concrete world by an invented conception which they take to be more real than nature itself. Thinking like this turns naturalism into its opposite. Much that passes for naturalism and physicalism these days are instances of transcendental folly. So the second chapter of Smolin's section, Principles for a Cosmological Theory. The idea that an acceptable cosmological theory needs to be formulated in a framework different from that of the so far successful theories of physics is not new. There is a tradition of critique of Newtonian physics, which leads to what is often called the relational position on the nature of space and time. Relationalism is associated with Leibniz, Mach, and Einstein, and in the present period, Barber, Rovelli, and others. Much of the critique concerns issues that only arise if you aspire to a theory of the whole universe rather than part of it. General relativity is partly, but only partly, as I will explain, a response to that critique. The roots of relationalism. We can draw criteria for a true cosmological theory from that tradition of critique. The starting point is Leibniz's great principle as following. The principle of sufficient reason. For our purpose, we state it thus. For every question of the form, why does the universe have property X? Thus, there must be a rational explanation. This implies that there should be a rational explanation for the selection of the effective laws we see acting in our universe, as well as for any choices of initial conditions needed for that universe. This application of the principle of sufficient reason was echoed in Peirce's insistence that nothing is so need of explanation as law. My view is that we should take the PSR, that is the principle of sufficient reason, as an aspiration and a goal, perhaps never to be completely reached, but nonetheless a beacon illuminating the direction in which we are to search for the answer to cosmological questions. We can state this as follows. The principle of differential sufficient reason, PDSR. Given a choice between two competing theories or research programs, the one which decreases the number of questions of the form, why does the universe have property X, for which we cannot give a rational explanation, is more likely to be the basis for continued progress of our fundamental understanding of nature. In this form, the PDSR is best used as a means to evaluate progress or to judge the likelihood of success of competing research programs. It is useful in judging the promise of novel research programs. The PDSR is especially helpful in cases which the PSR acts to resolve a question by removing it from the list of questions that the theory must answer. The paradigmatic example of this is the debate between Newton's absolute conception of space and time, and the competing relational notions put forward by Leibniz and Mach, and instantiated in a dynamical theory by Einstein. Here the question to be removed was, why did the universe not start 5 minutes later? On a relational account, this question does not make sense. Whereas in an absolute account, it both makes sense and is unanswerable rationally. Thus, by removing the question for which sufficient reason cannot be given, a relational account increases sufficient reason. This standard argument implies that the PDSR implies that space and time must be relational rather than absolute. In Einstein's hands, this led to general relativity, which definitely was progress. In this book, when I refer to the PSR of Leibniz, I will mean the PDSR. More generally, the PSR insists that there be no ideal elements or background structures in the formulation of a truly cosmological theory. These are structures or mathematical objects which are specified for all time, have no dynamics, participate in no interactions, but are necessarily to give meaning to the degrees of freedom that are dynamical. Examples of such ideal elements are Newton's absolute space and time, and the Hilbert space of quantum mechanics. Einstein formulated this as the demand that there be no unreciprocated actions. These are instances where an object A acts on an object B, which, however, does not act back on A. We call this Einstein's principle of reciprocal action, PRI. In contemporary physics, we distinguish between background-dependent and background-independent approaches to quantum gravity. and prefer the latter for being closer to the principles of relationalism. Examples of the former are the perturbative approaches to quantum gravity, based on fields or strings of moving on a fixed background geometry. By this time, several background-independent approaches are proving more fruitful. These include loop quantum gravity, group field theory, causal dynamical triangulations, causal sets, and quantum gravity. Another consequence of the PSR was stated by Leibniz as the principle of the identity of the indiscernible. That is, if two elements in the world have the same set of relations to the rest of the world, or identical properties, they are in fact a single object. There cannot be two distinct objects in the universe with the same properties. This rules out symmetries in the sense of global symmetries, that is, transformations, which take a physical system between two physically distinct states which have the same values of all conserved quantities. Many systems studied in classical and quantum mechanics have symmetries, including the standard symmetries of Euclidean space or Minkowski space-time. In every instance, these can be taken to be instances where an isolated system is moved relative to an external frame of reference. These symmetries thus make sense in the description of an isolated subsystem of the universe. But the principle PII insists that the universe as a whole has no symmetries. This implies it can have no non-vanishing conserved quantities, because by Noether's theorem, the basic conserved quantities, energies, momentum, and angular momentum are consequences of the corresponding symmetries of space-time. General relativity gets these right. A system can only have conserved quantities or symmetries in general relativity. if it has a finite or infinite boundary, where external boundary conditions are imposed. This is how an isolated subsystem of the universe is treated in general relativity. When general relativity is applied to a spatially compact universe, there are no global symmetries and no conserved quantities. It is then proper to regard the great conservation laws of physics of energy, momentum, and angular momentum as emergent and approximate. So one way a cosmological theory must differ from the standard dynamical theories of physics is that it must have no global symmetries or conservation laws. This does not rule out gauge symmetries, which are entirely different, as these take the description of a single physical system to a mathematically different description of the same system. The realization that a cosmological theory has no symmetries runs directly counter to a methodological slogan that the more fundamental a theory is, the more symmetry it must have. This imperative governed the progress of field theory for a bit more than a century, from Maxwell through the standard model of particle physics. But it has since failed us as a good guide, and it is more important to emphasize that what went wrong is that the imperative of more symmetry pointed to the construction of unified models of physics beyond the standard model, which were falsified by experiments. Two major versions of this were grand unification and supersymmetric extensions of the standard model. Each of these theories implied new phenomena as well as natural energy scale at which those phenomena would be expected to be seen. The experiments built to discover those phenomena have now pushed the limits beyond the scales naturally indicated. So, as you can see here, the stop in thinking is in knowledge itself. It is not in the world, it is not within me, It is in thinking itself, in the structure of how knowledge developed since antiquity, and how it was majorly transformed by Newton and his successors. So to speak, history had someone taken a certain turn and demanded eternalism. It's how knowledge was constructed or formed before. So it's an inevitable direction, which I think most people are not happy with, but it doesn't seem to be a choice. Smolin agrees there is no choice. Unless you start thinking completely anew, and you start with that time is real, because he certainly convinced me. It is ludicrous to say that time is unreal, or demand anyone to tell what time is. The reality is part of experience, and there is no exaggeration to say that physics have no left reality, especially when it comes to the grand design physics, not the details, but the project as expounded by, for instance, Michio Kaku with his string theories, or different eternalists like Hawking, and also relationalists like Rovelli. Although Rovelli is halfway to Smolin, there are a lot of parallels there, and Rovelli can indeed help you to understand what Smolin is getting to. A pleasure. This is most interesting. Sometimes I've been taken aback when I do these lectures, but especially now when we go into these things. The utmost realization, time is real, will end this lecture. Thank you very much for your patience. Bye-bye.